Here we're creating a simple model of a copolymerization reactor to demonstrate solution for a batch reactor that's isothermal. We're given how many kilograms of each of the two polymers are added. First order reaction in A and B. The thing that's different is the stoichiometry, and this says we're making this long polymer chain, and on average we have 1 molecule of S for every 3.2 molecules of B that form this long chain. Now, to simplify the calculation, we're going to assume constant density, but keep in mind this may not be a very good assumption. We're going from a monomer to a polymer, and indeed we could count for the density change, which affects concentrations and therefore affects rates of reaction. But for this simple model, we're going to ignore that, but keeping in mind that might not be a good assumption. Now, batch reactor, we're assuming even as we make the polymer and it gets more viscous, that still it's well mixed. So let's first make a diagram that represents what information we know about the system. So I've listed the information that we know, what our unknowns are, and then what we're going to do are mass balances, and we'll do a mass balance on each component. The mass balance essentially saying the accumulation of that component is how much is flowing in, how much is flowing out, how much is generated by reaction, where it could be positive or negative depending on where it's reactant or product. We're making balances on the reactants. The change in the number of moles of styrene respect to time, so N sub S is the total number of moles in the reactor. Well, the first term is 0, the second term is 0, and the third we'll write is the rate of styrene times the volume. And from our rate expression, the stoichiometric coefficient for styrene is -1, so we have a rate constant, which is the 0.036, concentration of styrene, concentration of butadiene, times the reactor volume. Same type of balance, there's no flow of B in and out, so it's rate of B times the volume. So for the mass balance for B, I have to take into account the stoichiometry. So 3.2 for every mole of S that reacts 3.2 moles of B. Concentration of S, concentration of B times the volume. Now I can make a simplification. Number of moles of S, concentration of S times the volume. I'm going to substitute that back in here. Because I assume constant density means the volume doesn't change, that means I can bring the volume outside of the derivative sign when I make this substitution. And so then you can see the volume cancels. So the concentrations after 10 hours can be independent of the volume of the reactor. Same type expression now for component B. For this case, we're going to end up solving this numerically to demonstrate how to do so. This is a simple enough problem. We wouldn't have to do that, but it's certainly much easier to do so. And so to do that, we need initial conditions, which means that T equals 0, the concentration of S is some initial concentration, and the concentration of B is an initial concentration. We're going to have to calculate this from the information that we're given, and what we're given is how many kilograms are added. So the concentration of S initially, we have 2,200 kilograms in 27 cubic meters, so we can calculate the molecular weight of styrene, 104 kilograms per kilomole, 0.78 kilomoles per meter cubed. And of course we can do the same thing for now for B. And so now we have our initial conditions, our differential equations, and we're going to solve this numerically in screencast part 2 for isothermal batch reactor shows the numerical solution.